today is in fact the last lecture of the course. As is tradition every year, in the last lecture we cover some special topic. We will let you know later whether today's topic is at all in scope, final exam. There may be one small question about it or nothing at all. We'll let you know in a separate announcement because we're recording this lecture in advance. Either way, so semester to semester we can change topics, and this semester the staff decided to cover something called interactive proofs. This is a topic in actually computational complexity, and the connection with this course is that we've been looking at how do we efficiently solve computational problems via algorithms through the semester. However, another way to interpret the question of solving a problem that has proved to be extremely fruitful is by the way of a protocol where you can think of the person trying to solve the problem receives some help by a third party, like some sort of untrusted prover that is helping the so-called verifier to check some computational statement, and by virtue of receiving help by an untrusted third party is actually able to check problems that it wouldn't be able to otherwise check on its own. Okay? Interactive proofs, and then show one non-trivial interactive proof for a problem that is not even known to be an NP. So let's get started. So today's lecture is going to be about interactive proofs. And first, as a motivation, we're going to first talk about, or maybe as a motivation, we're going to first discuss how to view the class NP, which we have seen several lectures ago, as a formalization of we can call it standard proofs. By standard proofs, so I will make that precise in a moment, okay? And interactive proofs will be some sort of counterpoint or generalization of the class NP in a very specific sense. So let's write down the definition of NP. The last time that I defined NP in this course, it was relative to the notion of binary relations. Now, typically, it is defined relative, and at that time, it was more convenient because they're easier to cast as binary relations. Though today, I will define it in the classical way, which is with respect to languages. Okay, and like I'm sure at this point you will have seen languages as used in various homeworks and also in the complexity notes that our staff has prepared. So the definition of NP, that really the canonical one, is as follows: a language L. Remember, a language is just a possibly infinite subset, a possibly infinite set of finite binary strings. Language L is in NP if there exists a polynomial time algorithm V, and also there exists a polynomial P. Okay, it's just a polynomial, such that for every instance in the language, there exists a proof that is not, or let's use witness for now because we talked about witnesses. There exists a witness of polynomial size, okay, so of size P of x, that makes this algorithm V accept. So V on x pi equals 1. And for every instance outside the language, no matter which witness you're considering, again of polynomial size, then the verifier will say no. Okay? So this is the canonical definition of NP. So now we can sort of look at this definition, and we can actually notice that in a very precise sense, we can interpret the class NP as basically saying, okay, let's consider all statements that have efficient proofs. Okay? What does it mean, efficient proof? Well, it says like this. I have an x. I'm wondering whether x is an L or x is not an L. Now, the statement x is an L, I can interpret this as a, more space here. I can interpret this as saying a true theorem or statement. Whereas saying that x is not an L, I can interpret this as saying a false theorem or statement. Okay? And here we're saying that all true theorems have a proof, so which I'm going to suggestively, instead of calling a witness like we have so far, I'm just going to call it pi. Okay? To kind of signify it's a proof. And actually here I already wrote pi without thinking about it. So there is a proof that will convince the verifier that the statement is true, the theorem is true. But for every false theorem, no matter which proof you're going to write, there is no way you can convince the verifier that the statement is true. So in some sense, L could be viewed in an abstract but precise sense as basically some set of axioms and inference rules that determine which of L will say out of all possible finite binary strings, finite length binary strings, okay, there's like all of them, some of them are true theorems and some of them are not, and that's what L is. And if there is a way to distinguish between them using short proofs in a way that is efficient, using the verifier algorithm V, then that class is an NP. So if you think about standard mathematical proofs like the one you've seen already in middle school and high school, where kind of you prove, I don't know, that two triangles are congruent, or you prove that some kind of the proofs that you write in sort of mathematics courses all the time, they have this structure. You kind of have fixed already an axiomatic system, basically axioms about set theory, and use inference rules like modus ponens to kind of derive new statements from other statements. Like if A implies B and A is true, then it means that B is true. Okay, so that's one way to kind of derive new statements. I could, in principle, set V to be the verifier that has hard-coded in it sort of the axioms of set theory and the mathematical rules for inference. And we could consider X, we could try to parse X as a mathematical statement, as a theorem, right? And the proof would just be the candidate proof, and the verifier would just be the way you normally check a standard mathematical proof, by basically starting from the axioms and trying to see if by applying rules of inference you're able to obtain the theorem statement from the axioms. Okay? So in a very precise sense, this is saying that actually we can model classical mathematical proofs, like Greek-style mathematical proofs, using the class NP. All right. That's why kind of just saying, well, that's just standard proofs. Okay? And notice they're so-called non-interactive because it's a written down proof that the verifier looks at. And crucially, it is important that the verifier is efficient. That is indeed the case when you try to verify a mathematical proof. You have this kind of very basic rules. And each new statement is a very simple derivation from earlier statements or the axioms. Okay? But very abstractly, this is what's happening. Now, a revolutionary idea in theoretical computer science that goes back to the mid-'80s is to investigate kind of proofs that involve interaction. Okay? So the picture here is that your verifier V, which receives X as input, previously would only receive this non-interactive proof pi. But now we're going to another entity, usually denoted P for the prover, that actually engages in a conversation with the verifier. So they exchange messages. So A1, B1, A2, B2. So this is just a conversation. And at the end of this conversation, the verifier decides whether to accept or reject. So it outputs 0 or 1. Okay? And with this in mind, look, a language L is in, so the complexity class that we consider now is IP for interactive proof. Okay? If there exists a polynomial time, now interactive algorithm, and actually I want to write this definition a little bit more with more space, so let me do it up here. A language L is in IP if there exists a polynomial time. Now it's an interactive algorithm V, okay, such that, well, what? We can try to do by analogy with NP. In the good case, for every x in L, we're going to say there exists not a non-interactive proof, but an interactive prover, P, okay, such that it makes the verifier accept in a conversation. So there's a notation that is often used for that. We use this angle brackets that says P and V will interact in a conversation. And we say that this conversation results into the verifier outputting 1 with that notation. Okay, so when we say P talks to V on input X, equal means that at the end of the conversation, V will output 1. Okay? And then for every X not in L, no matter what interactive prover you consider, okay, it holds that P and V of X, when they chat, makes the verifier output 0. Okay? Now, this is not actually a definition. We're going to come back to it in a moment. So let's kind of compare NP and the definition I have so far. So the picture that we have in NP and IP differ in the following way, right? So the prover in the definition of the class NP is kind of implicit. We don't really need to talk about it. We just talk about the output of the prover because that's the only thing he will ever output. Okay, so we just don't talk about the prover. There's no need to discuss it. But because in an interactive proof, the prover may answer as a function of previous messages, then we really have to talk about it as an algorithm that is part of the definition. Now, there is one point that we need to understand here, is that so far, if the interactive algorithm V is deterministic, there is actually no reason to consider interactive proofs. Because if the prover already knows what the verifier is going to say in the first message, in the second message, and so on and so forth, he knows that in advance, so he can just send a proof pi non-interactively that already contains everything he was going to say for those messages. The notion of interaction makes sense only, the notion of interaction is distinct from NP only if we consider the case where the verifier is probabilistic. So here I'm going to add probabilistic. Okay, so now we have the verifier as being probabilistic. This means that the verifier doesn't necessarily always output 1 or always output 0. So we need to put some conditions of the probability that he's going to output 1 or 0. Now, in the good case, we want to say that the probability that he outputs 1 is 1. Namely, he is always convinced. Okay, when X is in L, there is a way to write down this interactive prover that will discuss things, and at the end of the interaction, because X is a true theorem, he will accept with probability 1. Now, in the bad case, we want to kind of say that the probability that this happens is not big. Now, typically, we say at most half. That feels big, right? But if you think about it a little bit, you will notice that kind of this half is mostly arbitrary, because if you it, you can just run the protocol multiple times. And if you run it twice, the probability is at most a half. Sorry. I'm going to say probability that is 0 is at least a half. I'm going to say that it's large, okay? But if you don't like this probability, then you can just run it multiple times and reject if the verifier ever says 1, right? And this probability will kind of go exponentially closer to 1, which is what you want, okay? So this is a very natural notion. It actually is, to some extent, surprising and interesting that this notion wasn't formulated until very. So this good case is something that is called kind of completeness. This is basically saying all true theorems, there is a way to convince the verifier that they are correct. And this property is called soundness. Okay? And it says that there is no way for false theorems to make the prover convince the verifier with high probability. Okay? Because there's a false theorem. And this completeness and soundness are exactly the interactive probabilistic analogs of the completeness and soundness of the non-interactive proofs that we discussed, that are part of the definition of NP. Now, here the analogy kind of to algorithms is that the verifier wanted to solve a computational problem, okay? And without the prover, we've been designing algorithms all semester to do that. The algorithm receives an algorithm, or the algorithm receives an input for some computational problem, and computes. At some point, it outputs a solution. Maybe it's always correct. Maybe it is approximately correct. We've seen maybe it's correct with high probability, and so on and so forth. The notion of interactive proofs introduces this auxiliary party, the prover, okay? And actually, we think of this interactive prover as an unbounded entity. Has all the resources in the world. We're just trying to see, can the verifier check this, even if it has access to some, think about it as a wizard or like some god or somebody that is not constrained by sort of computational resources at all. All right. So IP is a class. NP is a class. IP is a class that is more general than NP. So kind of it's easy to see that NP is contained in IP, right? Because in particular, the prover could just send an NP proof, right? And the verifier can just check it. And this will be always correct on one side and will have no error on the other. A fundamental question that was studied as soon as this notion was introduced in the 80s was what languages are in IP? In particular, is there anything outside of NP that is in IP? So let's try to understand this question. Namely, are there languages or computational problems that do have interactive proofs, but for which we don't believe, or it is highly unlikely that they have NP proofs? And intuitively, it feels like that should be the case, because as also students, we have this kind of strong intuition that kind of learning from a textbook, for instance, studying by yourself, is you can only go so far. But with the help of a teacher, you're actually able to do a lot more. Somehow, just by this process of going back and forth and being able to ask questions buys you something. And that's like an experience that probably all of us have had, right? And here is actually a computational complexity question that exactly captures sort of this flavor, right? Can we do more with interaction in terms of solving problems than what we could have done with just non-interactive proofs, right? This is kind of like textbook studying and studying with like a teacher. So now I'm going to give an example of a cute computational problem that is not believed to be an NP, but for which we have an interactive proof. Okay, so we're going to see an example of how this thing works. So we're going to talk about so-called graph non-isomorphism. Okay, so let's introduce this problem. So let G0 and G1 be graphs on the vertex V. Okay, so we have two graphs, G0 and G1. They're on the same vertex set V. They just potentially have different edge sets, okay? Definition. We're going to say that G0 and G1 are isomorphic, and we denote G0 congruent to G1, okay, with this kind of 3-bar equal sign. If there exists a permutation pi of the vertices such that the permutation preserves edge relations. In other words, UV is in of the first graph if and only if pi u and pi v is an edge of the other graph. Okay? And sort of the intuition is that kind of pi is reindexing the adjacency matrix of the graph. Okay? Right? So if you kind of scramble the adjacency matrix of a graph, you will get potentially a different graph potentially, right? But if you scramble it in following a permutation, you should get a graph that is isomorphic according to this definition. And pictorially, it may be something like I don't know. So you have a graph. Maybe this is a graph of the vertices A, B, C, D, E. And I could flip B and C, and I would get two graphs that are isomorphic. I mean, the adjacency matrix of this graph and this graph are different. I should kind of the adjacency matrix of this graph and this graph are different. They just kind of have different names, okay? But there is a way to kind of scramble one into the other, preserving edge relations, okay? So now we're going to define a language, graph isomorphism. This is not yet the problem that we want to study, but just for analogy. The language graph isomorphism is the language of pairs G0 and G1 such that G0 is isomorphic to G1. Now, this language is clearly in NP isomorphic. One way you can convince me of that is you just give me the permutation that connects them, and I can just go ahead and check this condition for every edge. Okay, I can just basically for every edge in one graph, you claim that the graphs are isomorphic. I apply the permutation and see, is this edge also an edge in the other graph? If I do it versa, and this is an efficient computation, then I have certainly determined whether graphs are isomorphic. So this is in NP. Also, GI is not known. Graph isomorphism is not known to be in P. Namely, we do not know of a polynomial time algorithm that is able to establish whether they're isomorphic. Now, it doesn't mean that GI is NP complete. Lots of evidence that GI is not NP complete. Weird things would happen if it was NP complete. In particular, there is an algorithm that is almost polynomial time, so-called quasi-polynomial time, and that's GI. Now, but the problem we want to study today is its complement, okay? The language G and I, okay? So you give me two graphs, and now you're asking me, are they not isomorphic? Okay? So you want to convince me, you want to say yes when they're not isomorphic and no when they are. Now, just like GI, G and I is not known to be in. If GI had been in P, then certainly G and I would also be. Or even in NP. Because now it's kind of not clear what am I going to do if you give me like a witness to check that the two graphs are not isomorphic. To check that they're not isomorphic, it seems like I may have to check all possible isomorphisms, all possible permutations between the vertices, and rule out and establish that none of them are in fact an isomorphism between the two graphs. Because, again, like so, what would the proof be? Okay, so G and I is not known to be an NP. Nonetheless, we're going to look at a very cute theorem. One of the earliest interactive proofs discovered. We're going to prove that G and I has an interactive proof. Okay? So this is one language, potentially outside of NP, that we're going to discuss now, that has an interactive proof. So let's see. So you have the verifier. It receives G0 and G1. Okay? It has access to a prover. Okay? And the verifier wants to kind of engage the prover and get the help to establish whether these two graphs are isomorphic or not. So remember earlier I said that interactive proofs make sense only provided that the verifier is going to use some randomness. So now we need to kind of come up with some way to use randomness to kind of decide G and I with the help of a prover. So here's what the verifier is going to do. It's going to flip a bit at random. So it obtains B, which is random bit. And it's also going to sample a random permutation. Okay? So it takes a random permutation. So random bit B, random permutation. Now it's going to compute a graph, let's call it H, which is the permutation of GB. Namely, if the bit B is 0, it will permute at random G0. And if bit B is 1, it will permute at random G1. Okay, so far it hasn't done anything with the prover. Now it's going to say, hey, prover, here is the graph H. Which graph do you think it is isomorphic to? The prover is going to have a guess. I mean, it's going to have to figure it out. We'll talk about it in a moment. Let's say at some point it says, I think it's isomorphic to graph GB tilde. Okay? And now we're going to just check whether the prover was correct. Now, this is a very beautiful, simple protocol. What is intuition here? Look, if the two graphs really are not isomorphic, then because the isomorphism is an equivalence class on graphs, then H, it will either be isomorphic to G0 or G1, but not both. And P, because it is computationally unbounded, can figure out which and answer. On the other hand, if G0 is isomorphic to G1, then H actually carries no information about B, because whether you start with G0 and you permute it at random, or you start with G1 and you permute it at random, because G0 is isomorphic to G1, H will be just a random graph in the equivalence class of isomorphic graphs isomorphic to both G0 and G1. So P will have no idea what to answer. No matter what he does, he will convince the verifier with at most half probability. Okay? So I'll go through this one more time more carefully by writing it. But we just argued that this is an actual interactive proof. So let's do it. Again, so if we want to prove that this protocol is an interactive proof for GNI, we have two properties to show: completeness and soundness. Completeness says that if the two graphs are not isomorphic, then there is a way to make the verifier accept all the time. Let's see. Let's suppose G0 and G1 are in GNI. Namely, G0 is not isomorphic to G1. Then H is isomorphic to G0 or G1, but not both. Cannot be, because if it was isomorphic to both G0 and G1, then G0 and G1 would be themselves be isomorphic to one another. Okay? But we assume that's not the case. Therefore, the prover can figure out B, namely, if H is isomorphic to G0, it will answer B equals 0. And if H is isomorphic to G1, it will answer B equals 1. And answer this B tilde equals B. Now you may ask, okay, but how does the prover figure out which graph it is isomorphic to? Well, that's the prover's problem right now. That's not what we're not considering that now. Our focus is on making sure the verifier is efficient. The prover being efficient, it's a different story. We can talk about interactive proofs with efficient provers and what can you do with them. But that, again, that's a really different story. Right now, we're not worrying at all about the prover. We're just trying to see whether the verifier can be fooled by any prover. But here, I'm saying there is a way for the prover to answer in the good case. For soundness, we're going to say, suppose that G0 and G1 are not in the GNI language. Namely, they are isomorphic. In this case, then H is distributed, rather, the distribution of H carries no information about B. Another way to view it is that the random variable H equals pi, or rather the random variable pi of GB is the same as the random variable pi of G0, which is the same as the random variable pi of G1 for random pi, okay? Because G0 and G1 are isomorphic, it doesn't matter which of the two I'm starting from. Just the mere fact that I'm applying a random pi says that all these things are like the same thing, okay? So no matter what the probability that B tilde equals B is half, right? Because the prover has no information about the bit B. It's kind of hidden. H doesn't carry that information when G0 and G1 are isomorphic. And so he will not be able to convince the verifier with more than half probability. Okay? So this shows that this protocol is an interactive proof for graph non-isomorphism. A couple of comments about it. One interesting feature about this protocol is the fact that it uses this fact that the prover P, in one case is unable to kind of learn about the bit B, and that's why he's unable to cheat the verifier, to fool the verifier. So this is something that is known as a private coin protocol, which means that the verifier hides some of its randomness in order to gain an edge over the prover. In this case, it hides B. But actually, it turns out that this is not essential. There is a much less straightforward protocol that is something kind of, well beyond the scope of this class. Some ideas on universal hashing. That's the subject that we discussed in the lecture on dictionaries. That actually constructs an interactive proof for GNI where the verifier keeps nothing secret. It only speaks randomness to the prover. And at any moment in time, the prover always knows all the randomness of the verifier so far. So it looks like this protocol is it relies on this secrecy of the randomness of the verifier, but it turns out that actually it's not essential. But this is something that we're not going to talk about in this course. All right, so notice that, so the punchline is that even though GNI, for all we know, is not in an NP, there is no short, possibly very clever, non-interactive proof pi that makes the verifier accept. However, there is a very straightforward and simple protocol that with just one round of interactions, a little bit of randomness, the verifier is able to check the non-isomorphism of two graphs. So now that there is some evidence that interactive proofs are useful for a verifier to check languages outside of NP, question is, okay, how much more beyond NP can you go? After all, maybe graph non-isomorphism is maybe not such an interesting problem. In fact, it's not such a hard problem to begin with because we know there is an algorithm to decide without any proofs whether two graphs are isomorphic or not. That is almost polynomial time. So it's kind of right at the edges of P for all we know. But so now what I'm going to do is I'm going to mention some, this is the last lecture, so I'm going to mention some facts at high level with some intuitions that hopefully should give you an intuition for why actually interactive proofs are much more powerful than NP. So let's consider a language that should be fairly, so we call unsat, so sat bar. Okay, so we've seen SAT in class, right? That was the language of satisfiable Boolean formulas. Let's look at the language of unsatisfiable Boolean formulas. Okay, so this is all formulas. There's n bits to 1 bit for some n that are not satisfiable. Okay, namely, no matter what you plug into the formula, it always outputs 0. Okay, it's never satisfied. Now, here is a theorem that I'm going to state and roughly talk about only at very high level, is that unsat is actually has an interactive proof. There is a way to check that the formula is not satisfiable. Now, the rough idea is that you're going to reduce a problem of the form for every a in 0, 1 to the n, phi of a equals 0. Right? This is what it means. This is exactly what it means for the formula to be unsatisfiable. Okay? And by the way, this is also this type of condition seems very much unlike NP. It seems like very far from NP. I mean, how could you imagine that this problem is an NP, right? You would have to potentially check. It's not like SAT, right? That you're trying to find this one thing that satisfies. Here you want to say, no. Like, I actually want to check that all possible assignments do not make the formula satisfiable. There seems to be like no NP proof, but there is going to be an interactive proof for that. And the idea is that we're going to reduce a problem that looks like this to an algebraic problem. That has the form, well, let's look at the sum over all Boolean inputs of some polynomial that depends on a formula A and is the sum 0. So we're going to start with a condition like this that says for all possible inputs, the formula is unsatisfied. And we're going to cook up from the formula some polynomial, P. And we're going to ask, is the sum of this polynomial over all Boolean inputs 0? Okay? And then it turns out that actually there is a beautiful and a sort of seminal result in interactive proofs that says that this problem has an interactive proof. So it has a name, the interactive proof. It's called the sum check protocol. Okay? It's a descriptive name because we're kind of checking a sum. Okay? The sum check protocol, something that maybe would take a lecture to describe by itself, it is not that complicated, is an interactive proof that even though the sum is over 2 to the n inputs, the verifier is actually able to check this statement exponential speed up. Okay? So again, the verifier is trying to check an exponential sum, right, over 2 to the n inputs, but the sum check protocol will let the verifier check it only in poly n time, which is kind of what we want. Now, we're not going to discuss this protocol. I encourage you to kind of look it up. It's a sort of fundamental piece of theoretical computer science. I just want to highlight that there's something very interesting happening here, that we've turned a problem about Boolean logic to a problem about polynomials. And this process is known as arithmetization. It's a sort of umbrella term that denotes a special type of NP reductions that basically take all kinds of problems and cast them as questions about polynomials. And the properties of polynomials are exactly what enables this type of speedups. Okay, they play an important role, mostly because polynomials are related to something called codes, which you may error correcting codes, which you may have encountered in some of your EE classes. Now, turns out that so this is already like a much more powerful statement that GNI is in IP. You can actually take this further And you can actually prove that not the class unsat, but it's something called sharp-sat is in IP. What is sharp-sat? Sharp is saying, don't tell me whether there is at least 1 or 0 satisfying assignments. Convince me of the exact number. Okay, actually, let me write that better up here. So in fact, one can prove that sharp-sat is in IP, and sharp-sat is the language of pairs phi, let's say v, such that the number of satisfying assignments of phi is v. Okay? Notice that this problem is strictly harder than sat and not sat. And the rough idea is actually basically similar. We're going to turn a problem such as sum over a in 0, 1 to the n, sum up all of the assignments, and we're going to turn this into some problem about a corresponding polynomial. It actually turns out to be a slightly different polynomial in this case to this one, and then run the sum check protocol. Okay? So if you haven't taken a class like 172, just to appreciate how difficult this problem is, you may want to kind of look it up. It is a very difficult problem. It is very conjectured to be very far away from NP. And yet, we have an interactive proof for it. In fact, things go even further. And so I'll mention, where do they stop? So the characterization of interactive proofs is captured by a well-known and celebrated theorem, an equality known as IP equals P space. This is an equality that says that the languages that have interactive proofs are precisely equal to the languages that can be solved in polynomial space. Okay, so this says all languages solvable in polynomial space. This is an enormous class. Let's just first understand it. When we solve polynomial time algorithms, now an algorithm that runs in polynomial time certainly has polynomial space, right? Because it only had polynomial time to do things, so its memory will never have, its memory usage will never have been more than a polynomial space because it ran in polynomial time. An exponential time algorithm may also use exponential time space, but it doesn't have to. So kind of P sits, so P space is this kind of middle class between P and exp, where exponential time, that says you are allowed to use exponential time, but please don't use more than polynomial space. Okay? And there are many natural problems that very difficult problems that are complete for this class. I'll give you one, sort of an n by n chess. So n by n chess is NP complete. It is P space complete. So chess, by chess I mean specifically like the chess game on the what is it called, the 8x8 board. Is it 8 or 16? That's 8. If you take chess and you consider the problem given a configuration, this is like given a configuration does white or black have a winning strategy? So this problem, again, suitably generalized, to arbitrarily large boards, is p-space complete. So this is an example of a problem, and then if you've ever sort of tried to write or think about just how difficult this problem is to solve exactly, okay, then you might appreciate just how large the class p-space could be. Now the proof of IP equals p-space is that the sum check protocol leads to a very famous protocol. It's called Shamir's protocol. And Shamir's protocol basically is able to think about this alternating, for example, you have this alternating black, white, black, white, black, white, and you're kind of exploring this sort of very big tree underneath. And Shamir's protocol is able to kind of represent that question about exploring the tree as an algebraic question about polynomials. And this protocol lets the verifier kind of check whether black or white has a winning strategy from a particular configuration. These are kind of all things that are sort of beyond the scope of this course, but it does tell you that interactive proofs are extremely powerful. Now it's interesting that so all of this happened like in the span of maybe 3 or 4 years, like 5 years. In the second half of the 80s, a lot of things have happened since then, but something that is kind of particularly maybe compelling from an algorithmic standpoint today is that so 30 plus years later of I guess research in interactive proofs and related objects. So interactive proofs are not the only types of proofs that computer scientists study. There are like other types. Sort of all of this has led to this may look very abstract and not particularly useful, but today we're actually able to do in real world so some practical delegation of computation. Can really run and I can feel in your hands. So what's the problem? Say that you have a verifier V, like the one we discussed, and the verifier is wondering whether f of x equals y in t steps. So it has some difficult computation it wants to check. Maybe it's like some machine learning model, and it's trying to extract it by training it, and it just takes a long time. And it has access to a powerful cloud server, which it doesn't trust, and it acts as a prover. But the cloud server has a lot more computational power than the verifier does. So the verifier could say, you know what, like you do the computation, just tell me the answer and convince me that that's the case, okay? Because I don't trust you. So they're going to engage in some sort of interactive proof or some other related proof. And what we're able to achieve through kind of all of these techniques, especially things like the sum check, is that, well, the prover is going to have to run in time kind of proportional to t because it's doing the t-step computation. But the verifier is going to be able to run in time that is exponentially smaller, in polylog t. Okay? So log t is exponentially smaller than t. Polynomial in that, it means that the verifier has checked an enormous computation done by the prover exponentially faster. And this seems magical. I mean, it really does look magical. I mean, the verifier never did that computation. But underneath all of this, there are techniques that directly trace their lineage to arithmetizing computations, protocols like the sum check protocol, and basically statements like IP equals P space that tell us that a weak verifier that runs in polynomial time is able to check very difficult computations like, does white or black have a winning strategy in n-by-n chess? And given such statements, it is not incredible to think that the verifier may have exponential speedups for some computation it is outsourcing to the cloud. These are not just theoretical statements. There is probably by now tens of millions of dollars in venture capital funding in technologies that are doing precisely this for building all kinds of products. This is something that has happened in the last 10 years alone of developing technologies based on what are called probabilistic proofs. Anyways, clearly the second half of today's lecture was not very precise, so just take it mostly as for your knowledge and just a bit more fun. Today is the last lecture. A few things. So please don't forget we have a final. We'll let you know the format as soon as we know ourselves. By the time probably this recording goes online, we'll know. Please don't forget to fill in the course evaluations. It's been a pretty rocky semester for everybody, including the staff. And we would be particularly interested in knowing in which of the adjustments we made to the course you found were to move everything online were more effective or less effective, because our staff may find themselves in situations in the near future, and would certainly like to do a better job next time, because this time around we really found this on our plate unexpectedly. So feedback on this front would be very much appreciated. Otherwise, I hope that the disruptions in the semester were not too great. You managed to learn about algorithms nonetheless, and you had fun. And yeah, good luck on the final.